What's up, guys? So today I'm going to be talking about the FGSM attack, which is the fast gradient sign method attack, which allows us to take an image that a neural network might recognize as one class and switch it up, perturb it, and make it look like, to the neural network, a different class. So here in this example, this is our final goal. So to get from an image that looks like a 6, that's a 6, slightly perturb it and convince our model that it actually looks like an 8. So let's get into it. Before we start, I'd like to share with you guys a little PDF, LaTeX PDF I made that demonstrates how this works. So let me share my screen here. So the fast gradient sign method, FGSM. So it's a simple and powerful technique for generating adversarial examples. As we said previously, these are inputs to ML models that are intentionally modified to look like the model made a mistake, but actually we're just perturbing it, and even a human could know that it's unchanged and barely different from the original image. Now, review, and you can check out some of my other videos that I'll leave up here. Neural networks learn by minimizing a loss function, J, which is a function of theta, X, and Y. So what are these different parameters? So X is the input image, like our handwritten MNIST digit, like we saw the 6. Y is the correct label, so in our case it would be 6 or 7 depending on the image. Theta is the parameters of the model. So when you hear like an LLM that has 7 billion parameters, 11 billion parameters, these are all of the little knobs and sliders that decide how, when a neural network sees an image, how it might determine whether it's 6, 7, whatever. And then J is the loss function itself. So we'll use cross entropy loss, which is the most relevant for a classification problem. Now during training, we adjust and tweak theta to minimize J using gradient descent, which I talk about in another video as well that you can find on my channel. But FGSM flips this. We keep theta fixed. So let's say we have already found a theta that minimizes our loss, and we perturb the input X. So we perturb the image to maximize loss, causing the model to misclassify the image. So here's a closer look of what that looks like. So we have our image X, we have some perturbation constant, Epsilon, and then we have our gradient, so the direction in which our loss is going. So X prime or X mark, however you want to call it, is the new adversarial image. Epsilon controls how much we perturb each pixel. The gradient of the cost function with respect to the images is the gradient of the loss. And then the sign just takes the direction. So it takes the sign of each gradient component, positive or negative. So why does this work? So neural networks are incredibly sensitive, and even tiny perturbations in an image can make huge impacts in the classification. Because of the high sensitivity to high dimensional input spaces, we're working in the MNIST example with 28 by 28 images. So to a human, the perturbed image may look the same, but to a computer, because of its sensitivity, it looks completely different. Now a quick note on tuning. So epsilon equals 0. If we look back at the formula, it won't have any impact. Epsilon small will make small tweaks, and then a large epsilon is a very strong, but visual noise may become apparent, and the image might not be the same visually to a human being. It may trick the model, but it may not be the same visually to a human being. And ultimately, the goal is keep the image visually looking like a 6 in our example, but to the computer, trick it into making it look like a 8. And I'll leave this PDF down below if you want to look at it as I'm doing the live code demo, but the goal is today to make a very simple implementation of this attack and show you how to use it. I think it's a really cool attack, so definitely stick through the video if you'd like to see the coding part. So now we'll go to Google Colab and get started. Okay, so the libraries we need, we're going to be using PyTorch today. So we're going to be using PyTorch's implementation of a neural network. So we need a few of these torch functions, and I'll specify how we're going to use each one in a bit. We're gonna need transforms for image manipulation. We're gonna need MNIST for our data set. And then obviously these are the bread and butter. So the AI here already knows what we're trying to do. So these are the libraries we're going to need to use. Now let's try to make our basic CNN. So to make our CNN, we'll make a CNN class and use our PyTorch library. So we'll make a init constructor. Wow, Google Colab is so helpful. It's already giving us the code we need. We'll just use super, and we need a convolutional layer. So this is a convolutional layer with 1 input channel and 10 output channels, and then .conv2d 110 with the kernel size of 5, and then we need a fully connected layer for 10 classes. So self.fully connected. This is a very simple linear layer for our network, and overall just a very simple NN. And then we need a forward layer. X equals f.relu. Relu is our activation function. A max pool layer. This is all, a lot of these terms I'm going to skip on like fully explaining because I have other videos that explain them, and I'll leave them in the cards up at the top. And then we flatten our vector, flatten our image to a vector. So -1, 10 times 12 times 12. Return self.fc. This will be our final probability scores for our images. So I'll just write up here, create simple CNN, 1 conv layer, plus 1 fully connected layer. Okay, so we've done that. Now we are going to load in our MNIST dataset and start this attack. So here we go. I'm going to call this section load MNIST. So we want first to, we're getting our images from the MNIST library. So we want to transform those images from the PIL format, PIL images to tensors, so we can actually work with them. So we're going to define a transform. Transform equals transforms.toTensor, exactly what we want. Then we have our test data, MNIST root, exactly what we want here. So we want it to mount to our data folder, not train, download to our local data folder, and then use our transform to transform the images to tensors. Okay, and then we will create our model class, simple CNN. Oh, we don't want that. And then we will set the model to evaluation mode, no dropout layers, no batch norm or anything like that. Okay, so we have our data now, we defined our model. Let's try the FGSM attack on the first 100 samples of the data set. So I'm just gonna find some arbitrary epsilon, and then if you guys are curious, you can play around with it. For I in range 100, we're gonna have an image and a label from the test data. at the index that we're at. An image, we're gonna add a batch dimension on squeeze, so we know what batch we're in, and then image dot requires grad equals true. We're gonna allow gradient tracking so we can actually use that for the FGSM attack. So at this point here, we're at the FGSM attack, the execution of the attack. Output equals model image. Model will take in the image. Pred original. We're going to keep track of the original prediction is just the argmax of the probabilities. Now, if the pred origin does not equal the label, then we are going to skip, because we don't want to work with images that the model got wrong. We want to only work with, right here, we want to work with images that are easy for the model to classify. Okay. Now, we're going to keep track of the loss because we also need that. Cross entropy, our output, and then torch.tensor, our label. And now what we're going to do is we're going to zero out any gradient stored in the model, backprop, compute the gradient of loss with respect to the image, and then use that for the perturbed image. So should have put here model.zero grad, zero out the gradients. Then that should be down here actually, after we compute the loss. Want to make sure the indentation is good. Okay, model.zero grad, loss.backward, so we're going to compute the backprop. And now we're going to compute the perturbed image. So perturbed equals image. Remember the equation? I have it down here. Image plus epsilon times image dot grad sign. And now perturbed is going to equal torch.clamp perturbed 0 to 1. So we're going to clip the pixel values from 0 to 1 to stay within a valid range. And now we are going to rerun our model on our new perturbed image. So now we're going to use, say, advanced output equals model perturbed pred adversarial output. We're going to run this and get the argmax. Dim equals 1. Now, if the prediction changed, we succeeded in our adversarial attack. So if pred adversarial does not equal the label, print we succeeded in beating the NN. And make this an F string so that we can put the sample I. We'll put the label, original label, call this OG, and then within the string, new predicted adversarial. Okay, so to visualize the perturbation, I'm going to add a lot of the matplotlib code. I don't think that's so interesting or relevant. It's kind of boring. It's just a bunch of formatting stuff. So I'm going to skip that part and just quickly go over the results. So now we're gonna run and see how this works. And it looks like it's working great. So we see here this 2 still looks like a 2 to us, but the model classifies as a 4. We can see that here too. Originally, the blue 2 is the highest, And then we see in the orange after adversarial, the 4 is then the highest. And this is the power of the FGSM attack. I think it's one of the coolest attacks on NNs. You do have to have access to the neural network itself, but I really enjoyed learning about this attack, and hopefully you did too. And if you have any thoughts or questions, definitely leave them down below. Peace.